the routing. I'm not going to finish going through the last few examples I had on those slides. I don't have time today. But we are going to come back to that, and in fact, we're going to come back to that particularly because that's what you'll be doing in lab 4. So don't worry, we will come back to it. We'll just come to that fact at a time that more suits when lab 4 is going up, so next week basically. So there was, this is broken by the way, it's showing down here, but it's there. The very first thing to point out is that there will be we'll use all 3 lecture slots next week. The main reason for this is because on Tuesday, this is when I want to go through those distance vector examples because, as I said, it's for lab 4 and lab 4 starts on Tuesday. And then we'll do that tutorial and a partial lecture on Tuesday and then lectures, full lectures on Wednesday and Thursday. And of course, next week is the last week of me being here. And after the midterm break, midterm break, it's not called that anymore. After the mid-trimester break, Aaron will be taking it. Okay, so next week we will torture you by using 3 slots, but one of those will mostly be tutorial. Okay, so look, what have we seen so far in this course? Okay, layer 2 we saw MAC addresses, and as I've said a billion times now, MAC addresses are flat and unique and are used to identify individual machines on a local area network. The Internet protocol is about how to join up all those local area networks and make an internet. Now, internet stands for routing between networks. These networks are all run by separate companies, separate organizations, separate individuals. So the inter part and the net part shows where that distinction is. When we're doing internet routing, we're routing between other people's networks. We're just joining up their existing network. We don't really care what they do with their network. We just route between networks. And that's what IP layer 3, the IP layer is for, and that's what IP addressing is for. So IP addressing is about identifying these networks that you're routing to. It's a little bit more involved than that because the IP address actually identifies each system. So this machine has an IP address, the machine that's in the lectern here has an IP address. Well, sort of. And we'll talk about that a little bit more. So IP routing really details how we actually get from one network to another. Once you're within a network, routing to the individual machine depends on however that local area network handles it. Now, as I say here, IP addresses identify an end system sort of. IP addresses are used to route packets end to end, and we've got 2 types of IP addresses. We've got V4 and V6. Now, because V4 addresses are 32 bits, I can talk about them on a slide. V6 addresses, 128, very much harder to put on the slide, very much less interesting to look at. So I'm going to take you through IPv4, even though it's technically obsolete and being replaced by V6. We will talk a very small amount about V6, but really, being a bit unkind, V6 is just more bits. So there are obviously some minor differences, but fundamentally it's just a bigger address space. Fundamentally, okay, don't ever say that to me. Okay, we'll look like an idiot. Okay, so IPv4. What we've got here is, I really hope it's not working. This is really, really weird. Looks like I don't have any slides to make. Oh, hang on. Even though I reset the room, you would think rebooting your room with a hard reset would actually default this. I suppose I should put this on. No, it's flat. Right, I'll give up. Okay, so when we're trying to address something, we've got this sort of split here because we're trying to route between networks. We have this idea of somehow identifying the network we're trying to route to, and somehow identifying the node within that network. So somewhere in these 32 bits, there's a part of it that's going to describe the network, so we can route from network to network, but also describe the individual end machine on the network. So there's our 32 bits. And, you know, this could be an IP address. I don't want to spend the whole lecture talking 0000101. I don't want to do that. And in fact, nobody wants to do that. So that's why IPv4 is kind of nice to talk about in class setting, because the basic rules are fundamental networking, but it has some nice design elements in terms of how it's laid out. If you've ever done IPv6, it doesn't have it. So what we can do is we can break this 32-bit into octets. Okay, 4 lots of 8 bits. Now we all pretty much know what 8 bits look like. They're from numbers, you know, to 255, 56 values in total. And so what we can do is we can talk about that IP address, that 32-bit number, in dotted decimal. So look, 1, 2, 4, 8. 8 plus 2 is 10. Oh, it's the decimal value. 1, 2, 4. Hey, that's 7. That's the decimal value. And obviously these chunks here are the decimal value of these octets. So we just end up with this much more human readable address of 10.7.5.1. And because I've just said dots, I've spoiled the trick. That's what's called dotted decimal. Now look, it's not actually a real number. It's not a number that machines can manipulate naturally, because it's just a human representation of this binary number. But it makes it really easy for network engineers to sort of talk about these IP addresses, and in fact to type them in without making mistakes. This is somewhat more humanable than that. Now, of course, the next layer up, DNS, is even more humanable than that, because we put names on these numbers. But anyway, so the basis of this is dotted decimal form. It's not for computation, it's just so people can understand what on earth is going on. As I said, you can't do maths with this directly. And in fact, as we go through the lecture, this was the original design. This was all going to be nice and easy, but realities have made this somewhat more ugly as time goes on. So that's called dotted decimal. All right. So, network addressing. All network addresses, once we're trying to address or route between networks, is split into these two parts. The network portion, which represents the piece of wire, if you like, the local area network. We're naming the network. I shouldn't say naming it, we're identifying the network. And then there's the node portion of the address, which identifies a specific host. Now, when we're routing at the internet layer, we don't actually care about the host part, usually. Okay, that's the responsibility of the local area network that we're routing to from our internet. So, as far as the routing, internet routing is concerned, we really only care about this network portion that identifies that network. Now look, IP isn't the only way to do this. Novell, IPX, this is old and obsolete, that had 32 bits network identifiers and 48 bits host identifiers. AppleTalk, which is also obsolete, 16 and 8. Clearly that's ridiculously small these days. These aren't the only ways to do it. Oh, there's part of my picture missing. That's why it looks weird. So where we draw this line sort of depends on the proportion between the number of networks that we can represent with this 32-bit number and the number of nodes or machines that we can represent with this 32-bit number. And that is actually the basis of how they used to do the networking when IP first came out. Okay, so where do we draw that line? The problem with IP, and I shouldn't really call it a problem, because the real opportunity, unlike Novell IPX and AppleTalk, the really nice thing about IP is there is no set place to draw that line that separates hosts from node numbers. We can do it anywhere we like. And basically that line moves depending on how we're using it. So where is that line? Well, we can have lots and lots of networks. So as you can see, this side of the line is all networks. Probably should have deleted that node word. But only a small number of machines or nodes can be identified. We can go to the other end of the extreme and have lots and lots and lots of hosts on our networks. So our individual networks, our LANs are very big. but we've only got a very small number of networks we can identify. So those are the two kinds of extremes. Now, as I said, we can draw that line wherever we like, and we can draw it so we can represent what we need. Doesn't mean it was necessarily managed well, but that's how we can do it. So, the very first way people said, okay, look, we've got this routing IP layer 3, we've got an IP address that we can draw a line arbitrarily. How are we actually going to handle routing from one network to another? Because that's what I do. I care about networks, and I only care about routing between them. So the very first way they did this was divide that IP address space there up into what we call classes. Now look, this is obsolete, right? But this was how they handled routing originally, and telling this story actually leads you to why we do things the way we do now. So in this case, you have 24 bits dedicated to identifying the node, and 8 bits to identifying the network. So this is what they called a class A address. This was big, okay, 24 bits. And we could identify, in theory, 255 networks. Now, 255 networks isn't a lot for an entire global internet. So we only used half of it. And we called the next bit class B. So class B had 16 bits for network and 16 bits for node. So this is a nice compromise. We can still represent a vast number of networks, and we can still represent a vast number of nodes. So the idea was that this was for big, huge companies. IBM, Department of Defense, Hewlett-Packard in the old days, that sort of. Class B addresses here were for medium-sized companies, like university. Almost every other company you can think of. And you'll see some real examples of this as we get near the end of the selection. And then we had down here class C, which used 24 bits for the network and 8 bits for the one-on node. So clearly we can identify, around 255 machines, but we can have a lot of these networks. And these are for small companies. Now, remember, this was the original design. It got replaced. So I'm telling you about something that is historic. But this was the way in which people originally designed IP. And then we had two more, which were basically, why didn't that come up? We had two other chunks. One dedicated to multicasting, and one chunk that was reserved for future use. They didn't use it in the end. So the first thing we had to do is, okay, if I've got class A's, B's, C's, D's, whatever, how do I actually tell what this binary number is? How do I tell what class of address it is so I can know what to do with it appropriately? And the way we do that is by looking at the first n bits of this 32-bit binary number. If it starts with a 0, it's a class A address. If it starts with a 1 followed by a 0, it's a class B. So as you can see, look, each time you're dividing the address space by half. So half of all the addresses are class A. The ones starting with 1 will be split between these B's, C's, and D's. Same deal for the next, this one here. So for 1 followed by 0, that's class B addresses. A 1 and a 1 followed by a 0, that's again dividing the leftover half from class B, that's class C. And class D, those are our multi-class addresses, are 1, 1, 1, 0. So the idea of having these most significant bits is our router can come along and it can look at these and it says, oh, hey, I know what sort of class address that is. I can just look at those first few bits and I can decide what to do with this address or how to act appropriately because I know what class it is. So that was actually pretty important. So let's do some small computations. If we have 0 as the MSB, most significant bit, we have a class A address. Now remember, we've only got half of our 8 bits worth, so we have around 127 things we can address. It's actually less than that because we've got some reserved addresses. 127.000 is a loopback address. It loops back to this machine. It's used for testing. and 0 used to be the old broadcast numbers. Once we exclude these, we end up with 1 to 126, which is the addressable range of Class A addresses. Remember, if these bits started with a 1, then this half was A, Class A, and the other half, 1, whatever's, were reserved for the other classes. I've got a picture coming up that will make more sense with that. If we have a 1, 0 as the MSB, most significant bit, we've defined this as a Class B. And if you do the math on those numbers, this gives us a range of 128 to 191. So these are the decimal values, okay? This is the value of the first octet. So we're only talking about that first octet. So I'm just going to go back to Class A. So if the octet starts with 1 through to 126, we know that it's Class A. If it's 128 to 191, we know it's a Class B. So this is just how the routers are doing it, and this is just the dotted decimal version, so you can see that there is a distinct relationship. Anytime you see a 192 to 223, we're talking about a Class C address. Alright, so here's a summary table. I'm not going to go through this is here for your reference, but there's the split between host bits and network bits. These are the identifying class most significant bits. We use 1, 2, and 3 bits to identify the classes. This gives us 7 network bits for a Class A, 14 because we're removing those reserved ones, remember, the old broadcast and the loopback multicast as well. 14 bits, 21 bits. This gives us 126 possible network IDs for Class A, 16,384 for Class B, 2 million-ish for Class C. And I mean, look, when they did this in the 60s, they thought this was a lot. You know, it wouldn't be a problem because you only needed 6 supercomputers or 6 mainframes for the whole world. I'm exaggerating a little, but these still seemed perfectly reasonable numbers. They didn't really anticipate the incredible consumer growth of devices and therefore the requirement for IP addresses when they designed this. Also, back in those days, computers were 8-bit and 16-bit at the absolute most, so a 32-bit number seemed like a lot to handle. 128-bit or 256-bit address, for example, would be a crazy amount of work for routers at the time and computers at the time to handle. So this was very much a historical decision. With a Class A, we can have 16 million-ish hosts on our network. If we've got a Class B address, we can have 65,000 hosts on our network. If we've got a Class C address, we can only have a measly 254 hosts on our network. Right, so here's a picture. There's a picture. That's Class A. By the way, we're going to come back to a much more interesting picture about this in about 5 or 6 slides. Okay? That's Class B. So we've taken so this entire box here is the IP addressing range. First of all, we divided it in half. That gave us the Class A addresses. We divided the remainder by half, which gave us the Class B. We divided the remainder of that by half, which gave us Class C. And we have multicast there, and we have Class D there. Multicast and future use, I should say. That's Class D. Future use E. All right, so that's how we've split up the IP address space using this class system. It's the sort of divide and half thing that everybody loves to do because that's what's natural to do in binary. Doesn't necessarily mean the chunks are intelligently sized. Okay, when you allocate like this, you end up with this really weird jump. You know, here in a Class A address, you could have 65, oh, I can't remember now. You could have 65,000 machines on your Class B network. On your Class A, you could have 16 million. The jump between those two is enormous. The jump between 256 and 65,000 is enormous. So what you ended up with was massive fragmentation. a company that just popped over, I need more than 256 machines on my network, I've got 300 machines. Oh, look here, have an address space of 65,000. Oh, I'm going to waste quite a lot. It doesn't matter. So you see the basic problem with this scheme was this fragmentation. You had a lot of stuff left over that people couldn't use. All right, let's put that to the side for just a bit. I'll come back to it later with a much more exciting picture. Let's talk about how to actually route. Okay, here's a Class C address. Now, the very first thing I should mention is when you see these addresses, 192 whatever, they are actually special. There's another one at 10 and so on and so forth. So this is a Class C private address. This is an address you don't see on the real network. This is an address only used within a local area network. And these addresses should always be dropped by routers when they're sending out to the general internet. So these are what you call private networks. So when you set up your router at home or whatever, you're always dealing with these types of addresses, or maybe 10.1, whatever. They get dropped the moment that packet with that address leaves your home network. They just get chucked away. And they're private, and they're actually used to do things like network address translation. I'll mention that briefly later on. So anyway, all the examples I'm doing are using these private addresses, but don't expect to see them out there in internet land. If you do see them out there in internet land, something terrible's gone wrong. Okay. We can't use 255 because that's reserved for broadcast, so we have to end at 254. We can't use 0 because that's identifying our network. So .0 is the piece of wire. All right, so there's our router there. So let's have a look at what it looks like. We've got our 2 Commodore PET computers. There's another 2, and these 2 are on different networks. So there we go. This network here is a Class C network using these private addresses. This here is a Class A network using the Class A private network address range. And so what we want to do is we want to route, say, from this one to this one. So this is what the IP protocol does. It routes between networks to other networks, and they may not be the same size. And you'll see here, this router actually has a number of internet addresses. On this interface, which is our Ethernet 0 interface, it's got .1. That's identifying the router for this side. And on this side, we've identified it here too. So .1, .2, .3. So the router gets identified by its own IP address. And that's related to its Ethernet card. And of course, every Ethernet card on these networks has an IP address, or should do, at layer 3. Must do at layer 3. Okay, so this is what the routing table will look like. This is just like similar to what we saw with the switch, similar to what we saw with the distance vector. If I get something addressed to this network with a 0, I don't care about .3, I don't care about .2. Okay, things on this side only care about this thing as a big blob. This is a big blob. Something sending here doesn't really, it's going to use that to address the end system. But any routers that are in between, say, these and this, just treat this as a unit. Okay? And they do that by identifying the network. So that network stands for this whole thing, that piece of wire, or virtual piece of wire, I should say. So .0. Now, if this router receives a message to anything that starts 192.168.1, doesn't matter what the next number is, it knows that it should send it out on interface 0. If it receives anything for 10.1.1 point anything, it knows it should send it out on interface 1. So messages from this guy sent to 10.1.3, I missed a .1 in there by accident, please fix it. It sends it to this network, the router picks it up and says, oh, I know what to do with the 10.1.1. anything. I send it out on interface 1. So it goes out on interface 1, and then it gets delivered by the local area network, whatever protocol it happens to be using. Maybe Ethernet, maybe something else. Don't care. That's not our problem at layer 3. Okay. Now, Imagine you're a medium-sized company. You've been given a Class B address. This gives you 65,132 possible addresses that you can use for the individual machines. If you take the longest piece of wire that you can imagine, we call it an Ethernet cable, and put 65,532 computers on it, it won't work. You'll have too much signal loss, you'll have too much reflection, it physically will not work, even if you'd like to think it will logically work. And from a collision point of view, you wouldn't get any traffic anyway. So, you know, there's gotchas everywhere. So what we're going to do is we have to find a way to split our Class B address up into smaller pieces so we can divide up our 65,000 machines. We can't use switches because this is too many machines. We want to use routers. So what we want to do is split up our Class B address into further smaller pieces within our company. Okay? The internet doesn't care. We just have a chunk of numbers. It doesn't care what we do with. So we can split them up using routers. And this has the nice feature that anyone who's using the broadcast address, it can be kept within a particular subdomain or a sub-partition of our Ethernet address list. So if we've got a Class B address, it would be very nice within our medium-sized company to divide this, say, into 255 networks of 255 hosts. So you see this is aligning quite nicely with that dotted decimal form. And so what we do is we have one collection of 255 hosts, another one, we stick routers in between, and then we join it up with a piece of router wire, and we use some extra bits to determine which network we're talking to. So this top one gets a .1, .2, .3. So what we're doing is we're actually using those additional 8 bits in this octet to identify the network, and then this last set of 8 bits in this octet to identify the individual machines on each of these networks. So we've kind of done the same thing that happened from Class B to Class C, in that we've done a further division by considering more bits. It's similar, it's not the same numbers, okay? So we now have the same problem here. We've got a subnet here. So this is within our company, okay? Look, this is now just, you know, a portion of these. We're just going to take a piece out of this and we're going to look at it in a bit more detail. So I've numbered all of those. So this is .1, this is the router's IP address, .2, .3, and you'll notice the most important bit here is the 1. That designates this network as subnet 1. This network here is our subnet 2. Okay. Let's put that in the routing table. Now, this is a Class B address. It starts with a 1 and a 0. So our IP router says, oh, hey, that's a Class B address. That's a Class B address. Hang on, I've got 2 interfaces connected to the same network. It's because it doesn't understand that this octet here is actually being used to subdivide the network. We have to find a way to tell the router to do that. So I'm going to put a big X through that. We need an extra tool so we can inform the router that we've subdivided our addressing range. Because at the moment, it doesn't know. It just sees a Class B address and it doesn't know how to route. So we've got to tell it how to differentiate those two networks. And we do that by introducing something called a subnet mask. Now, subnet masks were not created to torture network administrators. They're actually incredibly simple. And all they do is tell the router how many of the extra bits of our class address are being used for identifying a subnetwork and how many bits are being used to identify hosts on that subnetwork. So this is what we actually want. We want a 1 there and a 2 there. Before we had zeros, okay? So we want this. This is what we want. And we need a subnet mask to actually enable us, or our router, I should say, to identify those subnetworks. So I've already told you how we do it. We do it with a subnet mask. So what the subnet mask does is as I said, it tells the router how many bits are network bits. how many bits are host bits. So in this particular example we had on the last page, we want to tell the router that the first 3 octets in the table are for network identification and the last octet is for host identification. Now look, it doesn't actually have to be even divided on those octet boundaries. We can divide within. It doesn't look as nice in dotted decimal form because dotted decimal form wasn't designed for that, but we can actually arbitrarily put that line anywhere using an arbitrary subnet mask. So what we do is we put a 1 in the subnet mask where the bits correspond to a network portion. We put a 0 where it corresponds to a host portion. And all we do is use the router to apply a bitwise AND to that address so it can separate out the bits in the network identification. Because the router only cares about identifying networks because it's routing between networks. So basically putting the 0s there blank out the host portion. So we keep the network portion with these ones, and we blank out the host portion with the 0s. And of course we can do our subnet mask at any boundary. So when you see something like a /24, a /28, all that's doing is telling you where the 1s stop and where the 0s start. /27 says that the first 27 bits are 1s. /26 says the first 26 bits are 1. And the rest is 0. So you see these horrible dotted decimal versions of subnet masks with strange numbers in it, like 76, and it doesn't make any sense. But when you think about it in binary, all you're doing with that slash number is telling you where the division between those network bits, which are going to be 1s for the router, and the host bits, which are going to be 0s, is. And that's just converted into the dotted decimal number, unfortunately. So here's some examples. The /8, hey, that's the same as our class A address. Okay, so our network subnet, subnet mask looks like this: 255.0.0.0. /16, class B, another octet's filled with 1s. Class C, /24, another octet is filled with 1s. See, your 24's there, your 16's there, your 8's there. That's just saying which of these bits are set to 1 and which of these bits are set to 0. And of course we can put that anywhere. We can do a slash at any value between 0 and 32. I mean, not 0 really. So we could do it after 1. So for example, a /25, remember a /24 is a class C, a /25 is a half C. And look, this is where your dotted decimal starts to break down. Now instead of this lovely clear scheme which we had up there in the early days, we've now got 128. That says it's a half C. If we do a /26, we've got a quarter C, because every time you increment this number by 1, we're doing a halving of the addressing range. So a /27 would be an 8th C, a /28 would be a 16th C, and so on and so forth. So subnet masks aren't scary, they're just bits, and the slash number says where the 1s go to. Okay, so look, I talked about fragmentation, okay? Fragmentation is bad. It wastes a lot of address spaces. So class A, B, and C networks all had wasted space. Look, and then what used to happen is you used to, if you were a big, huge company back in the old days, you used to just go to the Internet Authority and say, give me a /8, or give me a /16. And as I said, the jump between those two sizes of 16 to 65,000 is big. So if you've got 70,000 machines, you're going to end up wasting 15 point something around a million addresses. And we all know that IPv4 has run out. And it's run out partly because of this fragmentation and the way it was divided up. So when they realized this was happening back in the 1980s, I'm being very iffy about that date, they introduced something called classless interdomain routing. So before that point, you just looked at the class of the address and then your router could deal with it. however, we now have classless interdomain routing. And the idea of this was to reduce the size of routing tables as well as reducing this fragmentation that wastes address space. And the idea was that this was going to be a hierarchical scheme. Instead of IP address ranges being defined by the company that owns them, when we've got lots of companies, that's no longer going to work. So what they decided to do was break the world up into chunks. And each chunk would have a piece of address space, IP address space, or in fact lots of pieces of IP address space. And so what they did is, instead of this company-based model, which was the original one, is they came up with this idea of regional IP registries, RIRs. And these guys are allocated blocks of IP addresses that are for a particular region. So you can see this is where the geographical distributions come from. Now the idea is that these regional internet registries further separate the pieces of the IP address space that they're responsible for to smaller organizations that are part of that region, like internet service providers. And then ISPs, again, in a further step down the hierarchy, give portions of their allocated IP address space to individual companies and individuals. Now, the thing that really changed when the class system went away is that organizations have to prove that they have, or that they will have, the number of hosts in their organizations that matches the size of the IP address block that they give. This is because it was running out. Obviously, in the early days, that wasn't necessary. Let me just catch up where I am. So here's a picture. This is how the world was split up. These are the regional internet registries. North America, South America, Africa, Europe, and, Russia, and the Asia Pacific region. So 5. The idea is that the address spaces would be allocated to each of these, and then they would be used for routing. So if you get a packet from, say, New Zealand, and you're sending it to, let's choose Africa. Okay, it's when it goes up to a high enough level routing, the packet you're sending will contain destination address that router will look at and say, oh, hang on, I know that's part of the African set of IP addresses, and it will therefore get routed to that geographic region. It's not quite that simple. So this is the thing I was promising you. This is the IP address space. As I said, it's full. This is IPv4. It is full. There is no space left unallocated. But what's really nice about this picture is you can see the history of the internet. Look, we've got Hewlett-Packard, we've got Ford, we've got AT&T, we've got MIT, big university, IBM, with another AT&T, Merit, lots of US government. So look, you can really see the history of the internet here. Now look, remember how I said this was Class A? Well, those are all Class A addresses. Now look, the stuff down here, these have all been allocated to these local, regional internet registries that have then further subdivided these in their regions. So all of these ones here were claimed back from the companies they've been allocated to. These guys have more lawyers. And they've kept theirs. What you said, so here you see Class A. Half of the Class A address space was reallocated to these regional internet registries. A few of these were given up as well, but the vast majority of those traditional ones have stayed with the companies, or in fact the companies that bought the companies that had long-term historical rights to them. Class B is down here. And look at the degree of these allocation blocks. They were getting so desperate at the end that you've got these little tiny islands here, Asia Pacific, just a tiny, tiny chunk here, tiny chunk, because they were running out. And you can see as time went on, things that were allocated in big chunks suddenly became getting allocated to these regional authorities in smaller and smaller and smaller chunks. This was trying to deal with that fragmentation. Now look, honestly, that fragmentation will be occurring up here as well. But you can't see it because they own those. So that's class B. And class C is here. And then multicast and future use block is there. Look, quite honestly, you're thinking, why didn't they just use the future use block? But it wouldn't have really changed much. The rate of allocation of the IP addresses was accelerating at such a rate that even using this would have only been a stopgap method. So there really was no point. That was where they jumped to IPv6. So anyway, this is full. You can't buy IP addresses anymore. There's no more address blocks that remain unallocated by the regional internet registries. But I just think this is a beautiful picture, just showing how, as time went on, that they were getting smaller and smaller blocks to deal with that fragmentation. So this is all about the IP address space exhaustion. Sorry, this is a really hard to read slide. So about from the 80s, it was apparent that IPv4 was running out, particularly because of the stupid way they allocated huge blocks to companies. So this is what motivated the abandonment of those class A, B, and C to classless interdomain routing. Now, to do classless interdomain routing, you have to do something quite clever with how you're routing at higher levels. You didn't need to do that when you could use class addressing. So CIDR caused the creation of a new routing protocol called BGP, Border Gateway Protocol. Prior to that, they used to use something else called IPG, sorry. Things driving this growth were unprecedented growth, exhaustion was growth, always on devices, modems, ADSL, and things like that, mobile devices. They introduced pilot technologies to try and deal with it, those private network numbers I showed you about, those hiding behind network address translation. So you could collect a bunch of these private network addresses and hide them behind one IP address through a network address translation. DHCP, making sure that you weren't reserving unused IP addresses within your networks. Virtual routing, tighter control by the regional internet registries over the allocation of addresses. They had to prove that they needed everything that they wanted. Anyway, so the address size was increased from IPv4, 32 bits to 128 bits in IPv6. Which, if I remember correctly from the top of my head, was more than enough IP addresses for every atom in the universe. So it should be enough. And it obviously is a lot bigger, but it's going to take time. Now look, I want to talk a bit about BGP, because it's really important. You saw all those chunks in the geographic map that were kind of next to each other. Those can be aggregated. Okay, so adjacent /20s can be aggregated into segments. These things, those blocks that were split up, all have to appear within what's called a Border Gateway Protocol map. And the point is, as you go higher up the routing hierarchy to match that geographic region, more and more of these chunks can be aggregated. And you need to do this, otherwise the tables at the top would be massive. Okay, explosive. You have to have a router at the top that knew everything, every network in the world. You can't do that. So what you want to do is join these adjacent blocks together so you know, oh, hey, I've got this. I can push it down to the next layer down, and it understands how those two are separated. Okay? So it's really relying on hierarchy to control the information at the top. So BGP is the thing that does this. I want to show you a video because the man who does this is very excited. But the point is, the BGP is the de facto routing protocol of the internet. It uses a distance vector-like protocol that we just saw. And the important thing is BGP routes between autonomous systems. These autonomous systems are companies and organizations. So I'm going to show you this video. This is the bit where I forgot to plug the sound in. So, what is this? Sound. Let's see what happens.
What is the Border Gateway Protocol and how does it work? BGP is only the biggest routing protocol in the world because it has to be. It's the routing protocol of the internet. It has to find all of the routes that the internet has and carry them around the world. Now, this is not a protocol that's designed for mere mortals. This is a protocol designed at the service provider. So for example, this might be CenturyLink, who actually runs my home internet connection, and I would have my house sitting right here going up to CenturyLink. Now, at my house, I would have a router, but it would not be anything, well, okay, at a normal person's house, you would not have a real router. You would probably have a D-Link or a Linksys, or I don't mean to insult these by not calling them real routers, but they're not. So these routers have essentially a default gateway to the internet, and as I open my computer and go to cbtnuggets.com, my router just says, well, I'm chucking it out there because I have no idea. But now we're into CenturyLink's world. Now CenturyLink is responsible for looking at this massive routing table and getting me the right direction to CBT Nuggets website. So then how does CenturyLink know how to get to CBT Nuggets? Well, welcome to the magic of BGP. BGP allows CenturyLink to peer with its other service provider neighbors. Let's say we've just got AT&T and level 3, and now you start seeing this big mesh we call the internet forming, where everybody starts connecting to everybody and exchanging routes. Now BGP has a funny world to manage because it kind of manages this trusted and untrusted relationships at the same time. CenturyLink peers with AT&T because they have to. AT&T is not their company, it's just a partner organization that they've agreed to exchange their routes. But in no way does CenturyLink really trust AT&T because it has no control over their employees or no control of their routers. So first off, unlike all the other routing protocols, neighbors don't just automatically form. I have to go in and configure BGP neighbors. I have to say, CenturyLink, you will talk to AT&T, and AT&T has to say, and I agree, and I'm going to configure my side to communicate with you. Then both sides configure all kinds of policies that says, okay, I'm not going to let you mess me up, CenturyLink, and I'm not going to let you mess me up, AT&T. So they put filters like crazy on the routers to make sure, for instance, that AT&T doesn't let private addresses sneak through, or allow some other kind of address to sneak through that messes up my routing. Think of BGP like a friendly dog going through the neighborhood. You're like, ooh, I want to pet you, but I don't want you to bite me. That analogy only kind of works, but you get the idea, right? So BGP looks at routing as big picture. It's routing through a network the size of the internet, so it doesn't have the time to really look at individual routers. It says, I'm going to look at autonomous systems, which these things could contain hundreds of routers inside of them. So if this is you can now, we're no longer AT&T, right? If this is you, let's say you're a service router, or you have a company big enough to run BGP. I mean, maybe you're working for like an Intel or something like that, to where you've got giant internet connections here, you're hosting major services here where people are coming in to your system. To get access to those resources, you are literally going to receive hundreds of thousands of routes from all of your BGP peers, and now your system, your routers in your system have to figure out what are the best ones to choose. And it's not easy. BGP doesn't have a simple metric that says, oh, well, whatever's the fastest bandwidth, because it doesn't see all the bandwidth. It's not going to say, well, whichever is the bigger router, because it can't even tell what kind of router, what routers you're going through. It really has to look at a sophisticated list of metrics. Are you ready for this? I just grabbed this website just by doing a quick search for BGP best path, and you can see, step one, it's almost like, think of BGP as like having a bajillion routes, right? Think of you standing in front of a room of 1 million people, and you go, okay, everybody with a red shirt, you go home. Okay, everybody that has brown eyes, you go home too. Everybody, and you're trying to narrow this down of millions of people, you're trying to narrow it down to the one who you're going to give a gift to or something like that. That's what BGP has to do. So literally every single route's like, okay, let's see, does any of these have a higher weight? No. Does anyone have a higher local preference? Did any one of these routes, is it one that I originate? I mean, you can see this list just goes on and on and on and on. And obviously, we don't have time to talk through what each and every one of these things are. But by the time it's sent in, you see number 11, it's like, I will find the best path. I'm just going to go with a random roll of the dice and pick the router with the lowest neighbor address. So what it's kind of like if everything is tied, whoever has the lower IP address as a neighbor relationship ends up becoming the best route. So when you really dive in and learn BGP, you spend a lot of time looking at those metrics because each one of those are something that you can modify and you can tweak to make sure that your system, maybe as a service provider, as an enterprise customer, is choosing the best internet path. The last thing I want to mention is BGP is the slowest routing protocol in the world. Seriously. Everybody's like, oh man, it's so big, it must be like ninja fast, and it's not at all. Have you ever registered a domain name? That's like one of the most exciting days of your life as a new IT person, right? You're like, I've got, like for instance, I used to have the blog ciscoblog.com before Cisco took it from me. But I'm not bitter much. So when I registered that, I'm like, I'm so excited, I have the blog name ciscoblog.com, and it took days before it actually showed up on the internet. I was bummed because it has to be that way. People are registering domain name all the time. It takes a while before it actually shows up on the internet and all that. Same thing with BGP. You can't have, how many times does a network go down around the world? A lot. I mean, right then in that little pause, 100 networks just went down and went up, and BGP has to calculate for that. There's flapping internet routes all over the place. So literally, BGP is one of those protocols that's like, oh, network went down. Let's wait and see if it comes back up before I advertise it to anybody. Wait some time. No, it's coming out. Let me tell my neighbor. Neighbor's like, oh, well, let's give it some time. I mean, it takes time both to add a network or to remove a network from the BGP routing table. What I'll leave you with is this. Go to Google and type in BGP.
Okay, so the important thing is here, well, how does the internet even stay up? It's an incredibly fragile looking device. But the important thing there was how slow BGP has to be. It's not slow at routing, it's slow at finding new things, and it's slow at recognizing when things have gone wrong. Now look, I wanted to, maybe I'll do these during the tutorial, but ping you should all be familiar with. Traceroute, some of you may or may not. I'll show you that in the tutorial. And Looking Glass is where you can look up the regional internet registries lists of autonomous systems. And if you happen to feel like following that before I show you, if you look up, if you manage to find number 23905, that's this university, which is of course an autonomous system. In fact, it's got several entries. So it's worth having a play with those, but I will go through those on Tuesday as part of the tutorial. All right, thank you very much. The next lab will be out on Monday. Tuesday lab's been, right? Everything was working okay? Anyone in the Tuesday lab? Working? Oh, awesome. Okay, thanks a lot. Have a good rest of the week. Cheers.